This is a re-recording of a talk that was given to the Retired Engineers group in Adelaide on the 5th of February 2025. The reason for the re-recording is that we had trouble with the microphone during the recording. I'm Cornelis Jan Kikkert, or Keith as people call me. I'm an adjunct associate professor at James Cook University and also at Adelaide University. I did my PhD at Adelaide University and have been lecturing full-time for 40 years before I retired. Since then, I've been giving lectures at Adelaide University on the energy transition. I'm an electrical engineer. I've got no financial interest in any nuclear or renewable industry, apart from the solar panels on my roof. I want to make our grandchildren and great-grandchildren not have to pay many times for the decisions that we make at the moment. I want the lowest overall cost, reliable power, and in a sustainable manner, regardless of the technology. The information I present here is mine and does not represent the view of any organization I'm associated with. Let's look at the background. Worldwide, there are 440 reactors operating, a little bit above half in the United States, France, and China. There are 65 under construction, pretty close to half of those in China. Nuclear power produces 9.1% of the total world electricity, and that's growing at 1.8%. Australia does not have any nuclear power. The nuclear power is growing in China and decreasing in the rest of the world. Solar produces 5.5% of the total electricity and is growing at 23%. In Australia, it's nearly 20%. In South Australia, it's 28.5%. Wind is 7.8% of the total electricity, world electricity. It's growing at 10% per year. In Australia, it's 13%, and in South Australia, 43%. Coal and gas are decreasing at 0.3%, but there are 15 countries which produce more than 80% of their electricity using gas. In 2023, there were 55.7 gigawatts of battery. Half of those were in China, and in China, they're growing at 250% per year. Worldwide, they're growing 121% per year. Australia's got 3.2% of the world's battery, growing at 95%. In 2023, Australia had 1.8 gigawatt. Now it's got 4 gigawatt. So it's growing at doubling every year. In South Australia, the power produced by discharging batteries was 0.6% of the total power in 2023 and 1.1% of the power in 2024. So you can see that's actually growing quite fast. Baseload power is always on. Coal and nuclear are typical of baseload power. You can turn them down to about 40, 50 or 60% of the maximum power. They take 2 days to start and stop. The utilization factor they hope to get is about 90%, which means they're always on and you only stop them to repair or refuel. Load following power stations, we varies the power to match the demand from the consumers. Typically a gas jet engine, it can start and stop daily and flex down to 15 or 20%. So that is much more suitable to the normal power supply. A peaking power station provides short peak loads, and typically they're reciprocating gas or diesel plant. They're very expensive to run, but the utilization factor is less than 10%. So that's really just for peaking. Variable renewable energy, or VRE, such as solar or wind, is intermittent, but it's the cheapest form of power and non-polluting. Typical utilization factors are 25% for PV and between 30 and 40% for wind. Solar energy power plants, stored energy power plants, batteries, pumped hydro, heat. They get a very quick start. Batteries can run from 0 to 100% in less than 1 second, and they can run for about 1 hour or up to a week, depending on the type of battery that we have. Typically, batteries are used to store energy overnight, and batteries now have a bigger financial part of the pie than gas in the evening peaks. Demand-side management is where we adjust loads to match generation. We can control hot water services, air conditioning, pool pumps, electric vehicles, industrial loads such as smelters, in order to adjust the load rather than adjust the generation. Just some little clarification on definitions. Mega is million, giga is 10 to 9, or also called billion, and that's got various abbreviations, and that's why in this talk I use the G or giga prefix instead of billion. Tera is 10 to the 12 or a trillion. Nuclear reactors split radioactive materials to produce heat, to produce steam and drive a turbine. There is a moderator involved, which is material in the core which slows down the neutrons, and those slowed down neutrons can then cause more fission. Usually the moderator is water, but it may be heavy water or graphite. Control rods are used to control the reaction, and they're made of cadmium, hafnium, or boron, and they are inserted or withdrawn from the core to control the rate of the reaction. And also they can be used to stop the reaction, to shut it down. Coolants are typically water, gas, carbon dioxide, molten sodium, helium, and they're pumped around using electric motors typically, and normally it won't have more than typically 4 pumps or more for reliability, and you don't want to put them in a basement so that they can get flooded, as happened in Fukushima. The whole system is enclosed in a pressure vessel, and typically that's run at 150 bar or 150 times atmospheric pressure for pressurized water reactors. The different generations, the first generation is now obsolete. Second generation is typically a pressurized water reactor, and that's the most common type. Water is at up to 350 degrees Celsius at 150 atmospheric pressure to prevent it from boiling. If it boils, the reaction is reduced, and that's a negative feedback mechanism which makes the system safer. Generation 3 use CO2, molten salt, or helium for cooling, and use graphite rods for the moderation, or graphite moderation. They've got a higher temperature and are more efficient. Molten salt can be used as a battery, as a coolant to improve the load following of the whole system. Generator 4 are under development, and fast neutron reactors are one type of that. They use uranium-238 to turn into plutonium to produce heat, and that's 60 times more efficient for the getting energy from the fuel, and as a result it produces less radioactive waste. 6 generator 4 types are under investigation. At the moment, only one high temperature gas cooled modular pebble bed reactor is in operation in China. Fast neutron reactors are a variation of the fast breeder reactors that are are used to produce bomb material. The European Union requires new reactors to be capable of load following from 50% to 100% capacity at 5% per minute. Nuclear fission needs to be maintained, and that puts a minimum limit on the output. For pressurized water reactors, the minimum is 25% at the start of the refueling, and at the end of the refueling cycle is up to 80%. So you can only vary between 80% and 100%, not much variation at that end of the cycle. If there are many generators, we can average about 50% minimum, and typical start-stop are about 2 days. The typical efficiency of the reactor is 35%, just like coal-fired generators. Generator 4 type can be up to 45%. The heat can also be used for other purposes like district heating. The removal of heat may cause environmental problems. Large reactors, typically 1 gigawatt, produce less power in the summer and more in the winter, seeing that it's easier to cool in the winter than in the summer. Small nuclear reactors are up to 30 megawatt and can be made in a factory to reduce the installation cost. There are 2 in operation, 1 in Russia, 1 in China. None are commercially available, so it'll be about more than 15 years before they are. And there are many proposed projects, much hype. Fuel salt may be used to make a reactor that's a little bit more load following. Let's have a look at different countries. France is one country where, if we look at this, it's 90% of the energy is clean energy, and nuclear power is between roughly 80% of that, but it's falling. And it's falling because solar and wind are increasing. In Germany, they decided to phase out nuclear power, but they've got far less clean energy, and at the moment it's 50%, and 50% of that is wind. So wind is 25% of the total demand of Germany, and solar is about half of that. Both of these are increasing rapidly. In China, hydro has been pretty well constant, but the total demand is increasing, and also other forms of clean energy are increasing, so that the actual percentage of clean energy produced by hydro is falling. You can see wind and solar have overtaken nuclear as a share of the Chinese market. And even though China is building nuclear power stations, the percentage share of the market is falling because the other forms increasing much more rapidly. In 2024, 12 European countries had more than 80% of their electricity supplied by solar for longer than 1 hour. And you can see solar is really taking a significant part. Typically, the capacity of solar is growing something like 26%. So in France, nuclear dominates. In Germany and China, wind, solar, batteries, and hydro dominate. Let's have a look at the time and costs for large projects in Australia. And we're looking at 3. Project Energy Connect is a transmission link between South Australia and New South Wales, was approved by the South Australian government in December 1997. Estimated cost $95, was halted by the ETSA sale and then restarted. The planning so far has taken 5 years. Constructions initially was estimated to be 2 years, is now 6 years. So that's a 3 times increase in construction time. And also the costs have increased by 3.3 times. Snowy pumped hydro scheme proposed by the federal government, and seeing as federal government in national parks, planning approvals were very short, 2 years, but the construction time initially was guessed as 2 years, and it's turning out to be not more than 9 years actually. So it's a 4.5 times increase in construction costs and construction time, and 6 times increase in costs. Victoria to New South Wales interconnector, VNI West, is a 250 kilometre transmission line, and the planning is taking longer than 7 years, and there's had to be a lot of public consultation, and actually routes have had to be changed because of the consultation, and that's taking a long time. Let's have a look at the time and cost for building a nuclear reactor, and we're taking just some that might be fairly similar to what Australia is getting. The Flamanville reactor will be active soon. It's taken 17 years to build, and it's 7 years late at 4 times the initial cost, and is costing $13 per watt. Vogels 3 and 4 took 10 years to build, 2.8 times the initial cost, and $28 per watt. Olkiluoto took 17 years to build, 3.7 times the initial cost at $12 a watt. Hinkley C, estimated cost 12 years. It's not finished yet. The initially was scheduled to operate in 2017. That's many years ago. So it's 5 times the initial cost, and is now costing $57 per watt. And there's a further recent delay on how to prevent between 16 and 46 tons per year of fish being sucked into the cooling water inlet. So that's actually, the building is not progressing at the moment. On average, 9 of the recent reactors, the construction time was 13 years. The average capital cost was $16 a watt. And that's excluding Hinkley, which is an outlier at $57 a watt. All of those were built in democratic countries and all at existing nuclear sites. GenCost report reckons $9 per watt, and Frontier Economics, the modeling for the government, for the coalition, assumes $10 per watt, and the average, as I said, was $16 a watt. So Australia, they're all new sites. We've had no nuclear experience, so I would expect much greater than the 13-year cost that we have for the average reactors in countries where they do that all the time, in addition to the planning and approval time. So the coalition wants to produce 13 gigawatts of power, which they reckon will cost $300 billion, and the first one will be 11 years to be online. They need to purchase site, change laws, lots of planning and public consultation, environmental approvals. It'll probably take 7 years. AEMO says 8 years to get the laws sorted before one can start planning. Add that to the construction time, 13 years. Typical, we're looking at 20 years. GenCost is assuming more than 15 years, assuming less than 6 years to build. Now, the problem is, if we take 20 years, we're looking at 2024 for the first generator to become available. Will the coal generators that we have last until that time? At the moment, the last quarterly energy dynamics report from AEMO indicated that 25% of all the coal-fired power stations were offline, with 25 of those in an unplanned outage. Now, the longer over time that will get worse because the power stations are getting older. Waiting for nuclear will make the national electricity market a lot less reliable. The cost of transmission requirements, site purchasing, etc., hasn't been considered in any of the following costing. If we look at the carbon dioxide that we produce, the green curve is the present government assumptions. If we don't take out any of the nuclear, retire any of the nuclear power stations, till 2040 we get the blue curve, 2045 the red curve, and it costs roughly $500 per ton to remove the CO2, and the CO2 stays in the atmosphere. So the only thing you can do is actually remove it. So that's $874 billion for the first reactor starting at 2040. If it starts at 2045, it's $1,000 billion. Nuclear station estimated cost $133 billion. You can probably multiply that by 2 or 3. The decommissioning costs are similar to the build cost, but are not included in any of the costings. So the claimed cost is $133 gigadollars, but our children will have to pay at least $1,000 billion, depending on the time that the first nuclear station gets online. So that's 9 times the nuclear build cost not included. And if you think about it, that's a very expensive loan. The nuclear site, the sites that are nuclear stations supposed to be built on, 6. At the moment, they've got coal or had coal-fired power stations on them. There's 8.66 gigawatts, and they're going to replace that with 13.3 gigawatt, which will give 38% of the total power nuclear, and 54% renewables and 8% gas storage. None of the proposed sites are owned by the federal government. The owners do not want to sell. Most of the sites have batteries, either planned in construction or in operation. So sufficient power line capacity is not available. That'll take time and money to resolve, and they may even have to look at other sites. If we look at the amount of CO2, look at why we need to remove coal-fired power stations. This is a curve of carbon dioxide and temperature. The two match pretty closely. And we're looking in Australia at the moment, the 1.5 degree temperature rise, a little bit less worldwide. So any CO2 that's emitted stays in the air forever, or in the sea forever, and of course there's heat there. And that must be removed. Direct air carbon capture allows that to be done, and that'll cost, the estimates are that'll be $500 per ton or bigger by 2050. The shadow carbon price is $420 per ton by 2050. That's set by the federal government, and that actually matches that pretty well. A coal-fired power station, 1 megawatt electricity, costs yields $130 profit to the owner of the coal-fired power station, produces 1 ton of carbon dioxide, and our grandchildren will have to pay $500 to remove that CO2. Australia at the moment produces 440 megaton of carbon dioxide per year, and that'll cost $220 billion per year to remove. In addition to that, there's risk of tipping points, which are large permanent climate changes that you cannot reverse. So we must eliminate fossil fuel usage in all forms as soon as possible. The big question is, can nuclear power be a sensible part to the zero carbon transition in Australia? So how does nuclear fit in? If we look at the cost, nuclear is, according to the CSIRO, between $155 if it runs 90% of the time to $252 at the moment if it runs 60% of the time, which is what the coal-fired power stations do. By 2030, that's a little bit lower cost, $150 or $245. And we'll do some calculations based on the 2030 cost. Solar and wind with firming is a lot cheaper. And by 2030, it'll be $67 and $137. So that's much lower cost than that. So firm solar PV and wind is the cheapest. And both nuclear and renewables need extra storage and transmission lines. Decommission and waste storage is not included in the costs that have been mentioned. For nuclear, that's actually quite expensive. So this plot here is the plot of the present NEM wholesale price. That's the dotted line. South Australia is the solid one. Nuclear power stations, that range, and firmed renewable is that. So you can see firmed renewable are the same or less cost as the NEM is at the moment. Nuclear is more. The Hinkley Power C has got an agreed price with the British government that they've got to pay, and that's $271 per megawatt hour, when at the moment our price is $120 per megawatt hour. So frontier economics assumes a 1% reduction in building costs per year for nuclear power, but our home building costs are rising bigger than inflation. So I think that's a little bit wrong assumption. So in South Australia, and it's that red curve that you really got to look at, that's the percentage renewable. We've gone from 0 in 2008 to 75% now. And we expect 100% in 2 years' time. Adding base load is not needed. Existing wind and solar are the lowest cost, and nuclear will make a loss. The South Australian electricity is just what the national market will be in 10 years' time. And we can use that in our calculations. Right, so this is Australia, and Australia at the moment is at 40% renewable. And if we follow the trend, it'll be 80% by 2033. The ALP assumes 80%, has got a target of 80% by 2030. The coalition by 2050 want 54% renewables, when at the moment it's 39%. And they want 38% nuclear, 8% gas storage, which is now 6%. So they want no change in renewables pretty well, but big increase in nuclear. So the coalition plans to stop the rollout of wind, PV, and batteries. The wholesale price of electricity in South Australia is shown here between the 10th of January and the 17th of January, just a few bits ago. Average price for that time was $8.4 per megawatt hour, so a lot less than the 120 average. And just about every day, and you can look at this, open electricity, the negative prices during the day for roughly 25% of the time. And the nuclear power stations would have to bid negative in order to be able to not have to turn off. So adding nuclear will actually make these prices more negative. And if we look at the nuclear, that's the nuclear cost at the minimum output power that a nuclear station can produce. And in this period of time, it would only made a bare profit, a fraction of just during this time here. The rest of the time, it would have made a big loss. Now, other countries, Finland had 5% negative prices in 2023. Germany and France had negative prices, 5% and 8.3% in 2024. And those negative hours are doubling every year. So nuclear become less economic over time. If we look at those negative prices, South Australia is way ahead of the rest, and that's Victoria, New South Wales, Queensland, and that's New South Wales, and that's Tasmania. So if you think about it, between 9 o'clock in the morning and 3 o'clock, the sun shines, and that's when there's lots of solar power. So that's about 25% of the time. Nuclear must pay to produce power when the price is negative and compete with the lower cost of PV and wind the rest of the time. Baseload generation is a very bad investment. And it's interesting that the coalition proposed that the federal government owns the generators so that if it's a loss is made, then the taxpayer's got to pay. This is the plot over a month of the South Australian sources of energy, of electricity, over a day period, average over a day. You can see here, that's the rooftop solar. That's actually quite a big part. That's large-scale solar, wind. That's imports, and that's battery exports. That's the level of baseload nuclear power. You can see if we've got that, then all the time, some nuclear will need to be turned off in order to keep the base load going. And also even some of the rooftop needs to be turned off in order to keep the nuclear power going. On many days, in many days, the rooftop PV, in fact, is more than 100% of the demand. Renewables have produced more than 137% of the state's energy. So on many days, nuclear will cause forced shutdown of rooftop PV, forcing people to buy power from the grid. In addition, the minimum demand that we have on some days has been decreasing. So in 2015, this was the minimum demand, not much difference from the average because there wasn't much solar. Now there's a lot of solar. The solar power pushes that demand down. At the moment, we've got minus 232 minimum demand. There's 235 megawatt of solar installed each in 2024, and it'll be fairly similar in South Australia next year or this year. In the NEM, it's about 3 gigawatts. And so this curve will go down by about 230 megawatt each year. And that's causing problems for the NEM, because when we have negative power like that, and then you've got your 600 megawatt of base load wanting to force its way in, something's got to give, and we may get really big instability problems. This is the average peak demand and minimum demand during 2024, and also the average demand in 2015. You can see that this bottom here, this area has decreased and will keep decreasing as the power as more rooftop solar is installed. And you can see on average, we nearly have more nuclear power than the average power demand. So everything else got to be turned off. So to minimize the losses when the power is negative, nuclear generators need to be capable of load following, not just base load. And base load increases the losses for the nuclear owners. So the question is, can we turn down nuclear, or is it just a base load? Steam turbines used in coal and nuclear generators have a minimum recommended load of about 60%. AGL is modifying its turbines to operate at lower limits, and Loy Yang is 45%. In Bayswater, they've been able to get down to 30%. The lower power, however, means bigger wear and tear in the machine, and as a result, larger maintenance costs. So it's a compromise. You reduce your losses, but you increase your maintenance cost. For nuclear power stations, the same things apply. They also have turbines, but in addition, we've got the ability to control the reactor. If you use control rods, then you can go down to about 25%, which is also the limit of the turbine control. The French flex their nuclear power down to about 30% for load following. So 25% is the maximum you can turn it down. 30% is probably more economic for them. It's common to actually reduce the power that you produce by dumping steam, and that's just like idling a car. And that's actually may cause environmental problems. For stability, you must have the generator load and load in balance. Australia can't export power like France can. If they've got too much nuclear power, they can export it to Germany, Belgium, etc. If there's too much power, we need to either increase the load or reduce the generation. Batteries can increase the load by charging, and they can also reduce the output following using load following, or we can reduce the output using load following generation. We don't want base load. That's very hard to control and match to the variations that we have in the load. Grid batteries can soak up the excess nuclear power. If we've got nuclear power, that will be at negative prices. The batteries will then compete with nuclear because they're fully charged. They want to get rid of that power, and they compete with the nuclear at positive prices. So they'll eat the lunch and dinner of nuclear power at both ends of the price range. The choices are, we have baseload nuclear and renewables and storage, and that's a coalition policy, or we can have firm renewables with enough storage for dispatchable variable renewable energy. Or alternatively, that's actually the third choice, which isn't mentioned by anybody, we can have firm renewables and storage with nuclear load following or peaking plant, and the nuclear power would then operate at 4%, not 38%, and replace gas. And that would be by 20, replace the gas peakers. Which path should we take? The International Renewable Energy Association reckons that solar is $57 a megawatt hour, and the that's had a drop of 90% over 10 years. So it's getting a lot cheaper very quickly. Wind is $63 a megawatt hour, 70% drop over 10 years. If we look at the gen cost, we can see here in 2030, solar $37 to $63, wind $52 to $88, and nuclear $141 to $233, and we use that for some of our calculations. Solar and wind are quicker to construct than nuclear, as you can see there, and we don't need all that much storage per kilowatt hour in order to get 90% renewable energy. So for 90% firmed renewable energy, we're looking at $100 to $143, and there's not much difference in the cost for 60%, and that's because the cost of battery storage is actually very little, as we'll see next. Now, rooftop PV is economical for residents, and they will keep on installing that at about 3 gigawatt per year. So let's have a look at the cost of batteries. The cell costs have fallen 6 times to a factor of 1/6 over a 10-year period. Gen costs for 8-hour battery, they estimate in 2030 as $202 per kilowatt hour, and 2050 that will reduce significantly again. So if we do a rough calculation for 2030, have 10 years battery charge and discharge every day, that matches the typical sort of battery warranty for home batteries. The total cost then is $55 per megawatt hour. Plus we have the running cost, which is the difference between charge and discharge cost. And at this stage, for simplicity, we ignore maintenance and repair cost. So 3 different scenarios. If we charge at peak solar, we can always do that. We charge when renewables have all turned off, 0 cost, or we can charge at minus $100 an hour if we've got nuclear, and it'll probably be less than that. First of all, if we charge at peak solar, it costs $4 per megawatt hour for the electricity. If we charge at 0 costs, then we actually make a profit of $53 per megawatt hour. If we charge at the cost that nuclear's got to pay to stay online, it'll be a profit of $143 per megawatt hour. Now, $143 per megawatt hour is a lot bigger than that, so your battery actually really makes a good profit. So 25% of the time, big baseload nuclear makes a lot of loss, and the rest is small profit. The losses can be reduced by operating nuclear as a load following generator, so that you don't have to pay a lot of money to stay online. With baseload, nuclear will make a big loss and not a profit. Right, so let's have an actual calculation. If we assume the South Australian network last year as a model for our calculations. In that, we've got the local levelized cost of electricity in brackets in green, total demand as a percentage in green, and the average price in South Australia for that period is $126 per megawatt hour. Batteries, you can charge at minus $29 per megawatt hour. That's the average cost for that the batteries charged at. Over the period, they discharged at an average $257, so they made a $283 profit for the year. And they only produced 1.2% of the power, but that's growing rapidly. So if we apply all of these numbers, then for the NEM, scaling it to the NEM, and also the nearly 2 times increase in power demand using the step change, that's modeled. By 2050, nuclear at $150, which was the lowest cost, levelized cost calculated, and a 30% demand, which the federal government says it will do, they'll make $10 billion loss each year. Batteries will then do about 14.7% of the demand, and will make a $9 billion profit per year, plus they make profit on controlling the frequency of the network. Now, since you can calculate that nuclear is such a loss-making proposition, is this simply this proposal from the coalition a ruse to keep gas and coal in the national electricity market longer, and then in 10 years' time simply say, okay, well, nuclear is not economical, we'll just forget about it, and then actually start to roll out the solar and wind. And that's the question. So in conclusion, baseload power is a very bad fit for the NEM. Nuclear will need to pay to generate 20% of the time if it's operated the baseload generator. An electricity market will make, in an electricity market, nuclear will make a loss most of the time, and batteries will eat its profits. And someday, nuclear will cause rooftop PV to be curtailed, and people will be forced to buy power from the grid to keep the nuclear power stations running. The NEM will have a negative demand by 2030. Baseload nuclear generators will cause network instability, so baseload reduces the reliability of our network. Our children and grandchildren will have to pay 9 times the cost of the nuclear build for the CO2 removal, the decommissioning, and the waste storage. Vested fuel interests will keep trying to derail the variable renewable transition and push nuclear baseload power. And then on that, it's interesting, if you look at the website oil price, they're really heavily promoting nuclear power. Nuclear SMR with load following and quick start capability may be economical as an alternative to gas peaking. It'll have a very low utilization factor, less than 20%, so the levelized cost of electricity will be bigger than $800. And that needs a detailed analysis for cost. They do not yet exist and may be a few decades away, so we can revisit these calculations in 20 years' time. This year we must decide, continue installing firm PV, wind and battery, or stop the VRE rollout and install nuclear, which will make a loss each year, keep coal operating an extra 15 years, and saddle our children with a bigger than $1,000 billion cleanup bill. Anyone who says we need baseload power for low-cost, reliable power does not know enough about our current national electricity market. Baseload power will result in a higher cost for the taxpayer and consumer, and also will result in less reliability for the electricity supply. Any questions? Questions?
Yeah, hi, this is Hannes from 2XE. We're a consultancy up in North Adelaide. Essentially, I have 3 comments or questions. Thanks a lot for putting all this information together. I think it was very comprehensive. 3 questions or sort of, statements. One, I think, yes, this has been very to the point in terms of the development of the electricity demand, but I think we're also looking at a lot of new question marks in terms of the other energy consumption that we're having, that being EV coming into the question, and that also for productive facilities. We still have a steelworks up in Whyalla as of now. Where they're going to get their power from? So I think that's one. How's that all going to change? Two, I already mentioned EVs coming in, and I think that's positively going to change your equation because the cost of storage may actually be much lower if we can piggyback on people plugging in their EV when they're not moving around with it. And then the third question or comment on transmission. I believe if we combine solar with firm battery as you proposed, the need for transmission grids, I think, is a little bit, can be put to question because a lot of the generation is actually where the load is happening. So maybe you could comment on that again.
Well, with transmission, if you think about if we got variable renewable power, people say, yeah, but it's going to be cloudy and rainy where you are and you won't get renewable power. It might be raining in Queensland as it is at the moment, but it's sunny here. We can send power to them. In the winter, they send power to us. So having transmission lines averages out the relative few periods where you can't get enough solar or wind in order to supply the power. So, yeah, and that's an extra cost, and you've got to consider that. I've just looked at, I don't think you want to be here a week, right? We're just concentrating on a small part, but yes, in all cases, we need more transmission lines. And the federal government hasn't done much on transmission lines for the last 20, 30 years. They now have to do some catching up, and that's happening. Nassimi.
Nassimi Ertuğrul from University of Adelaide. I look at slightly different way, considering that we can now generate electricity locally most of the time. I guess one aspect is to address the load, residential load primarily. But before that, can we first of all look at decentralized system rather than centralized system, because it's possible. Other aspect is also related to the cyber security or power system security. I guess centralized system, nuclear, is more prone to those attacks in the digital world.
Talking about your local generation, that plot is the demand from my house. This is my electricity consumption, and I've got a house with 20 kilowatts of solar, home batteries, and for 260 days per year, I do not import any power from the grid. For 327 days, I export more power than I import. So yes, it's quite easy to actually make your home with very little energy consumption. And in a way, that's like a mini Saudosteli NEM, where most of the time I don't use any power, and I don't want to be forced to turn all that off to consume nuclear power. Yeah, having your own system is much more secure cyber-wise. I think no matter what you have, whether you've got wind turbines, large-scale solar, or nuclear power station, there are problems with the cybersecurity, and it's controlling the power network is becoming more and more difficult. And it is possible now for people to actually hack into that, and that is a risk. And yet the electricity industry has to be extremely careful to put the protections on to make sure things happen.
Who do you want next?
Well, whoever's the nearest.
Yes. Yeah, so in the initial slides,
when you are talking about the generators, so you said that the generator 4 have the highest efficiency, which is 45%. And then you talked about like some countries like Russia where the temperature is very low. So they use the heat generated to heat up the entire town or village. So, and then you said that heat removal may cause environmental problems. So I didn't
Yeah,
understand.
okay. So if you think about it, if we're going to put a 640 megawatt nuclear power station at Port Augusta at the top of Spencer Gulf in a very narrow area, in order to get 640 megawatts out, we probably have to about 800 megawatts of hot water that you put into the Spencer Gulf. That's a fairly narrow area. How are you going to dispose of that without heating up the environment too much to kill all the fish in that area? So that's the environmental problems I'm talking about. Hey, if you're in Finland, it's probably beneficial to some species, but not beneficial to others. And you've got the water cooling towers that they have, nuclear power stations, are enormous. So that's another way, rather than just sucking cold water in and just pumping out hot water, you have a cooling tower.
I'm going to wrap this up now. I'm sure that Keith will be willing to take all the questions you have afterwards.
Yeah.
But I'd like to ask Don now to give the vote of thanks.
Yeah.
Well, I'm sure that.
Don, stand here so that you're,
Oh, all right.
so that you're on the video. No, here. Yeah.
I don't know that I want this, but that's all right. Oh, okay, there I am. Yeah. Well, Keith, it's been quite an eye-opener. I guess the complexity of this is something we're all very much aware of, but having it expressed in numbers, which engineers, of course, love, casts a very different light on things. And I can't say, and I suspect many of us can't say, that we understood every single figure, but the way they are presented and balanced gave us an insight which I certainly haven't had before. And compared with the hype we get from so many vested interests, not to mention politicians, it's a welcome fresh air indeed to see somebody who has studied this in some depth and sourced reliable figures and presented them in a way we can sort of understand. It really makes a very great difference. Thank you, Keith. I know this hasn't been an easy task for you. It's been quite a job to put all this together. And we thank you most sincerely for this and for increasing our knowledge in such a major way. So I'd like to present you with, I hope it's one of your favourite wines, a Merlot, and wish you well. Thank you very much. Could you join me?
Thanks very much, Don. If anybody's interested, yes, it's taken me a month full time to prepare for this, doing lots of spreadsheets and lots of analysis. If anybody's got any other questions, I'm quite willing to answer them here.